And let's go back to the basic definition of a conditional PDF that we covered back in section 2.4. For any two random variables, no matter what they are, whether they're Gaussian or something completely different, the conditional PDF of x given y is always given by this formula. It's the ratio of the joint PDF of x and y at a particular value of y in this case, and it's divided by the marginal PDF of y at the specific value of y, which, as you remember from the previous section, it's actually the area of the cross section through that joint PDF at that given value of y. Now let's consider a couple of different scenarios here. First, let's start with the situation in which rho is equal to 0, which we knew, we've learned already that if rho is equal to 0, it means the random variables are uncorrelated. And in the case of Gaussian random variables, when they're uncorrelated, they have to be statistically independent. If that number rho is equal to 0, then this turns into the marginal PDF of x, and also if rho is equal to 0, when you plug it into the formula for the joint PDF of x and y, you get 1 over 2 pi e to the minus x squared plus y squared over 2. This is simply the product of the marginal PDFs, okay? F sub x of x times f sub y of y, which means that the random variables are statistically independent. Now I wanted to, in order to maybe help you to understand why this is true and what's going on here on a slightly different level, let's consider this from a geometrical perspective. Here is a graph of the top, from the top down, of the graph of this joint probability density function that I've got right here. 1 over 2 pi e to the minus x squared plus y squared over 2. The equipotential contours of this function are circular. In other words, for every locus of points on this graph for which x squared plus y squared is a constant, that locus will be circular. And what this surface, the surface corresponding to the graph of this function looks like in the xy plane is it's a mountain, sort of, with its peak at 0 at the origin. I often refer to this as a Gaussian shaped mountain. And consider what would happen if you were to observe a specific value of y, like maybe this value up here. Suppose we wanted the conditional PDF of x given that y is right here. That would involve taking a slice through the surface the way we did before, and if you took a slice or cross section through that surface, then what you would find is that it would look like this. Okay, again, this is a mountain, a hill with its peak at 0, so just slice through it and then look at it from the side, and you'll see it has the shape of the Gaussian curve. And if you normalize by the area under that curve, you get the PDF of x. Okay, the PDF of x is a bell-shaped curve with its mean at 0. One of the fundamental points to understand about this scenario when rho is equal to 0 is that because these things have circular contours, then no matter where you slice through it, in other words, no matter what the observed value of y, the cross-section will always have a peak at 0, and therefore the conditional PDF of x given y will always be the same bell-shaped curve with its peak right there at 0. That's an indication, another way of looking at the fact that these two variables are independent. If you observe that y is this value, or if you observe that y is this value, it doesn't matter to x. The PDF of x given y, doesn't depend on y, because the cross-sections are all the same shape. If it helps for you to see a 3D sketch of this, I tried to do this. I don't know whether this is any better or worse than what I had before, but if you take, again, this is a mountain with its peak at the origin there, and if you take cross sections through it at different values of y, what you get are bell-shaped curves, and they all have their peaks at x equals 0. Okay. Another way of looking at it, we didn't do this in the top view diagram, but if you were to take the conditional PDF of y given x, that would involve taking slices along parallel to the y-axis, and they would all have their peak at y equals 0. So x and y are statistically independent in that case. The top view for this example would involve the same sketch we were looking at here, but we'd be taking the slices in this direction, and we'd be generating Gaussian bell-shaped curves. I've stood them up on their edge here, like this, and the peaks you see would all occur at 0. So no matter where I slice through this, in other words, no matter what value of x I slice through it at, the peak would always be at 0 because these contours of this surface are all circular. And that would be that's why when you multiply the marginal PDFs together, you get this joint PDF. That's another expression of the condition of statistical independence. Okay, all of that pertains to the special case in which rho is equal to 0, in which we say that the random variables x and y are uncorrelated, and therefore they have to be statistically independent. Now, let's consider a different scenario. If rho were positive, not 0, but a positive number. Remember, rho can vary anywhere between -1 and +1. If rho is positive, then all of a sudden we don't have x squared plus y squared in the numerator up here anymore. We've got x squared minus 2 rho xy plus y squared, and instead of being the equation of a circle, that's the equation of an ellipse. And so the contours are elliptical, and if rho is positive, again for reasons that are I don't want to go into here, but relatively simple analytic geometry, the major axis is going to be the line y equals x. So these ellipses are lined up along the line y equals x. Now, let's consider doing something similar to what we did before. Suppose we want to see the conditional PDF of x given y, and we observe this value of y up here. We take a slice through this surface and see that the peak of this curve is no longer at 0, because this, instead of being, it's a mountain, if you will, but it's a stretched out mountain. Okay, maybe it's kind of like a mountain range or ridge would be a better explanation. The peak is here rather than over here, because this is the point at highest elevation through the cross section. That peak just happens to be at rho times y, as we found from the other equation. This is the conditional PDF of x given y, given we observe that y is equal to that value. By contrast, if we observed a different value of y, like down here, perhaps, and consider taking a cross-section through this surface along this line, notice that the peak would be, again, at rho times y, but y is negative here, so it's going to be over on the negative side of 0, on the left of 0. And so the conditional PDF of x given y is not always the same in this case, because the random variables are correlated. Rho is not equal to 0, and the conditional PDF of x given y actually depends on the specific value of y, and that means that the two variables x and y are not statistically independent. They're not uncorrelated, and therefore they're not statistically independent.